Greetings to Dr. T. My name is Yong Jin. We are from Section 1, Group 5, and we're going to present our experiment 6, which is the PID control systems. And our group members consist of Shafiq, Jensen, Dia, Baris, and also Yong Jin, which is me myself. So I'll talk about part 1, which asks us what and how the data will acquired and what are the dependent and independent variables. So the different output transient response from the block diagram for the engine speed PID controller system will be acquired in this experiment when different speed reference are used. And the data was acquired by double clicking on the scope of PID control system as well as applying the tools to obtain the setting time, the maximum overshoot, and also the steady state error. The independent variables are P, PI, PD, and also the PID controller, while the dependent variables are the setting time, the response time, maximum overshoot, and also the steady state error. While for 1.2, what and how the analysis will be conducted. So in this experiment, we'll be conducting using 3 tuning methods, which are the trial and error method, the Ziegler-Nichols method, as well as auto-tuning methods. Each of these methods have their own way of applying it. So the results, for example, setting time, the response time, and maximum overshoot, and also steady state error, will be all summarizing in a suitable table. While in 1.3, asks us to explain all the parameters involved in this study. We have the proportional value Kp, which if Kp is small, an error can be large, while if Kp is too large, the system may oscillate or become unstable. Next one is integral value Ki. Ki will remove the steady state error, improve the transient response, and also reduce the amount of overshoot. The integral action will take time to reach the desired value. Next will be derivative value Kd. The derivative terms can make the system more tolerant to external disturbance as the error is reducing. It reduces the drive to the plant and therefore prevents overshoots. Next, we have setting time, the time required for the response to become steady. It is defined as the time required by the response to reach and steady within a specific range of 2% to 5% of its final value. Next, we have response time. By dragging the response time slider to the right, will cause the response to indeed speed up, and Kp is now closer to the manual choose value. The second one is the maximum overshoot, where maximum peak value of the response curve measured from the desired response of the systems. While the last one is the steady state error. It's the difference between actual output and desired output at the infinite range of time. 1.4, what are the expected results of the coming experiments? The expected results are achieved desired setting time under 5 seconds and the steady state error to step reference input. The general effects of each control parameters on a closed loop system are shown in the table below, where we have the Kp. For Kp, we have the rise time to decrease, we have the overshoot to increase, while the setting time will have a small changes, while the steady state error will have a small decrease. While for the Ki, we have a rise time decrease, the overshoot increase, while the setting time will increase and the steady state error will decrease. While lastly, for the Kd, we have the rise times to have a small change. We have an overshoot that decreases and the setting time also decrease. And lastly, the steady state error will have no change on it. While for last part 1.5, build the required block diagram using Simulink. This is the block diagram, which will have a transfer function of 20 over s cubed plus 15s squared plus 10s. And that's all for my part. Thank you.
Hello and Assalamualaikum. My name is Awangku Shafiq. So today I want to make a presentation for our LAB6, that is PID control system. So today I want to show you for our part 2. So first I will use step, then sum, and P controller, and transfer function, and scope. So I will run. So this is the output that we get. So for the overshoot, it will be 36.301, and for steady state response will be 1.272. Next, I will show for the PI controller. So SAM will have step, sum, PI controller, transfer function, and scope. So I will run. So this is output that we get. So the overshoot will be 1.105, and for the steady state response will be 1.315. For PD controller, so I will run. So this will be the output. So for the overshoot will be 48.507, and for the steady state response will be 1.315. So lastly will be the PID. So I will change to PID controller, then I will run. So the scope will show for the output, that is for overshoot will be 0.510, and for the steady state response will be 4.358. So that's all for me. Thank you.
Hi, my name is Muhammad Farjazwan. So I will explain for the part 3 PID control experiment using Ziegler-Nichols method. So this is the basic Ziegler-Nichols formula. Next is the Ziegler-Nichols methods. From this we use the gain block diagram. So for our gain is 7.5, and then we run this scope, and then we get the for PCR is 1.975. Next is the Ziegler-Nichols method. For this, we can get the value for the Kp, Ti, Td, Ki, and Kd. Next, after we use that method, we can get the full value for the P, Pi, Bd, and the PID. So firstly, we need to find the P controller. So we just basically change the gain block diagram to the P block diagram. So we just change the controller to P and insert the value for P is 3.75, and then we run this program, and then we get the response. So for the overshoot, we get 71.552%. Next is the PI controller. So this step we just repeat from the P controller, and we just change the controller to PI and insert the P and I value, and then we get this response. So for the overshoot we get 202.500%. Next is the PD controller. So same step from before, and just change the controller to PD and insert the P and D value, and then run the program. We get the response, and the overshoot is 57.937. And lastly is for the PID controller. So we change the controller to the PID and insert the PID value and click apply and then run, and then double click the scope, and we can get this response for the PID. So the overshoot for this PID is 98.944%. So we can conclude that the Ziegler-Nichols method start by zeroing the integral differential gain and raising the proportional gain until the system is unstable. So the gain from Ziegler-Nichols will be higher than from other method. Among the P, Pi, Pd, and the PID, the PD controller is the most responsible for better result due to the highest steady state response in same setting time. So that's all from me. Thank you.
Hi, my name is Dia Akmal bin Ibrahim, and my metric card number is DE190064. Okay, now we continue at part 4, So part 4 required us to make a PID control experiment using auto-tuning method. So first we have to find all these component in the Simulink. So we use the PID controller, step, and also the transfer function and scope. So first thing, we have to connect all the component. So we connect all the component. Okay, after we connect all the component, we can click the run button. Okay, after it's ready, so we can go to the PID controller, double click the PID controller, and we click tuner. And this is the result for P controller that we use. So this is the parameter, controller parameter, and also performance and robustness. So at here we can see the all the rise time, settling time, overshoot, and all the data that we need to use in the lab. Okay, and after that we need to repeat the experiment with a different controller such as P, PI, PD, and PID. So we need to change this controller. Okay, to change the controller, double click the PID controller, and then we just click at here the controller and choose P, PD, PI, or PID. Okay. And then we click again the run button and repeat the step again to get the graph and also the data for the lab. That's all for me. Thank you.
Hi, my name is Chen Jensen, matrix number AE190080, and for this video presentation, I'll be doing the conclusion part and as well as the compiling of the whole report. So throughout the whole experiment, we have found that there's actually three methods that we can use to determine the tuning of the P, PI, and PDI controllers. So among which we have determined the try and error method, which is the most efficient one. So the first method, the Ziegler-Nicholas method, it is a little slower than try and error method because of the zeroing of the integer and also differentiation gain that consumes more time, whereas try and error method, it increases the derivative gain instantaneously. And that is all for this conclusion, and thank you.